Hello to all of you, dear friends. Welcome to the fourth session of this tutorial series. In this session, we're going to dive a bit deeper into the world of microcontrollers together and gradually start doing things that might not be so easily achievable just by designing circuits. In this session, so that we don't get too deep into C programming, since our goal here is to get familiar with microcontrollers, not to teach the C language, and also to help us get more acquainted with input, output, and various components. What I have planned for you is teaching how to work with a 7-segment display, which is actually one of the components that many people, myself included, find fascinating, because despite its simplicity, it displays the information you need. It has the cheapest circuit, the most compact circuit, and overall, it's an interesting component. Now, let's see how easily this component can be controlled with a microcontroller. So in this session, we're going to work with a 7-segment display, and ultimately the project we'll build is to have a counter on the 7-segment display using a single button, which is quite an interesting project. Alright, as always, we'll start with Proteus. The things we need to move this project forward are the microcontroller itself, the 7-segment display, and a button. We'll go ahead and add these components. As always, our microcontroller is the ATmega32. For the 7-segment display, all we need to do is search for 7-segment, and it will show us various types of 7-segment displays. What we need is the standard 7-segment display that's commonly available in the market. What you'll find in the market are these single units from this section. These ones at the top are just some binary display tools for Proteus, which we don't need to use. And if we look here, these are the standard 7-segment displays available in the market, which come in two types, common anode and common cathode. And here, it has also provided us with 3 color options. I'm going to use the common cathode model, and now it will also explain what it actually is. Okay, we've imported the microcontroller. We'll also import the 7-segment display and the button, which is called button here, and that's done. Alright, first I want to give you an explanation about how the 7-segment display works. Just like its name suggests, and as we call it, 7-segment means 7 parts. It's a 7-part LED, a 7-part display. If you counted segments, there are 7 pieces here that make up our number, and accordingly, we also have 7 pins here. Now, how are the connections made? If you consider each of these as a regular LED, it means each one is actually an individual LED. It's as if we've placed 7 LEDs side by side. If you remember in the previous project, what did we do? Of the 8 LEDs we used, one side of each was connected individually to the microcontroller. The other side was all connected together. They were connected to ground. This system is exactly the same. It's just like we've connected a bunch of LEDs to the microcontroller. So here we have 70 of those LEDs. Their negative sides are connected together and form a single pin. Their positive sides come out here so we can connect them to the microcontroller. And if we use or buy the common anode type from the market, it's the opposite, meaning the positive sides of the LEDs are connected together as a single pin, and their negative sides come out from this side to be connected to the microcontroller. So the system became very simple. From a distance, it might have seemed like a strange component, but it's really just this. There are 7 LEDs. Now, the ones available in the market have 8 pins for output because they also have an extra point here. But in general, we have 7 LEDs, and in the common cathode type, their negative sides are connected together and the positive sides come out. How is the connection arranged? If you pay attention to my mouse here, we have the topmost segment, and in order A, B, C, D, E, F, G. This is the order we have in a clockwise direction, and finally the middle LED. So it starts from the top and goes clockwise. And finally the middle LED. Now, for example, I want to show you something very simple. For instance, we want to display the number 1 on it. So as I mentioned, we have a common ground for the LEDs, which we connect. And now for the number 1, what is the arrangement? We need to turn on the 2nd and 3rd pins. So to turn on the 2nd and 3rd pins, I connect this. And you can see that it displays the number 1 Now in the same way, for example, I want to display the number 2. So the first 2 should be on, the next one is off. So we turn on the first 2. The next one is off. Again, 2 should be on. The next one is off, and finally the last one should be on. And you can see that it's displaying the number 2 for us. And this is how a 7-segment display works. Now we want to do the same thing automatically using a microcontroller. Let's go ahead and make the connections first. I'm going to add a microcontroller here. To make things easier, I'll use the same port again. Now to have a better orientation here, we'll use port C. And I'll make these connections. For now, these are all the connections we need. Since we're going to do a very small test with a switch in this session, I'll connect a switch like this. So up to this point, we have our circuit ready. Now let's move on to CodeVision, and I'll go through the project creation process again. This is so the process becomes completely clear for you. Now this will only take a minute of our video time, but it's good because you'll see the process repeated again. Here, as we said, we'll select the microcontroller again, and then go to the port section. In the port section here, specifically this particular time, we are indeed utilizing port C, and we are going to make use of 7 of its available pins. The 8th pin in this specific configuration does not actually need to be explicitly set as an output, so we are setting 7 of the pins belonging to port C as outputs. And on the other side, bit 0 of our port A is directly connected to the button and consequently should be set as an input. However, we currently have a pull-up mode enabled, which is a feature that is not commonly employed or utilized in many simulation projects that one might encounter. In the simulation, everything works perfectly and gives the right results. But then, in the real world, they see that the button doesn't work at all and picks up noise, and only then do they realize what should actually happen. And for example, this is one of the important differences between the simulation world and the real world. Which is what? That is a pin that is set as an input because it doesn't have any voltage applied to it and is left floating. In the real world, it picks up noise. Meaning, if that pin isn't connected to anything, it will randomly switch between 0 and 1, completely at random, and it doesn't matter whether you've pressed the button or not, because it's not connected to anything. It's constantly switching between 0 and 1 due to environmental noise. And for example, what kind of condition do we set in our code? Now, when one side of our button is connected to ground, it means that every time we press the button, we're applying 0 volts to the pin. In other words, it sets our pins to 0. So in our code, we set this condition. If the pin is 0, it means the button has been pressed. Now, what happens if the button hasn't been pressed? This pin picks up noise and randomly switches between 0 and 1, and the program thinks the button has been pressed. So we need to do something here so that when we don't press the button, meaning when our pin is free, it has the value we want, whether that's 0 or 1. If we want to do this outside the microcontroller, the way is to add a resistor, for example, like I'm adding here. The method is that we place a resistor and connect it to the 5-volt supply. What happens then? When we don't press the button, this resistor applies a 5-volt voltage to this pin, so our pin is always at logic high. And when we press the button, since the resistor is not in series, it takes priority over the 5 volts and brings the voltage of our pin down to 0, so that pin becomes low and our code detects that the button has been pressed. In this way, even when our button is released, with the help of this resistor, we are completely controlling the environmental noise. Now, the microcontroller actually has this same resistor built in. That is, as I said, many of these features are already built into the microcontroller itself. This is one of its most important features. For example, in your project, you might want to use several buttons, and in your circuit, you would have had to use a lot of resistors, but the microcontroller has provided this for us internally. So we no longer need to add this, and all we have to do is tell the code wizard to pull up this pin. Pull up means use that resistor to pull its voltage up. In more advanced microcontroller series, we also have pull down. That means with this resistor, bring the voltage down to 0, so that we have to set it to 1 from outside ourselves. So the terms pull up and pull down come from here, and here we just say pull up pin 0 of port A for us. So what does that mean? It means that by default it's 1. When we press the button, we set it to 0, and in the code we say that if it becomes 0, it means the button has been pressed. That's all we need to do in the code wizard, and now we run our code. Meaning, basically, we establish a new project for our work. By now you should be much more familiar with this environment, and everything should be a lot clearer for you. As always, I need to add a custom library here myself, and then we scroll down. Again, we can see that the code wizard itself is handling the pull-up function for us with the port. It's also handling the output operation for us using DDRC. So, what is it that we need here? It's this. We need to display our numbers on the 7-segment display. So to display the numbers, I'll use the same technique and code as before. From our previous session. Here I set port C equal to a binary number. And add a delay, for example, half a second. Then I want to keep repeating this. Now how exactly? Like this. For example, to display the number 0. Well, we've already seen together what happens here. Now these pins should light up in order, except for the middle one. So we go ahead and do this. And now, if we upload the code to the microcontroller, it will display the number 0 for us. Here, we can also see that the pin with the pull-up is set to high, meaning even if I don't connect anything to it, we see that this pin is set to pull-up mode, and in the real world, it won't pick up noise anymore. Alright, and in precisely the same manner, I can effectively display the subsequent numbers as well. For example, what exactly do I mean to convey? For instance, considering the numerical value of 1, we previously established that the very first segment should be in an off state, the second segment should be in an on state, and all the remaining segments should be in an off state once again. Now we see that it's showing us 0 and 1 repeatedly in a loop. Now, to display the numbers 0 to 9, you can implement the complete binary representation of the numbers in the same way, and it will be a really good exercise for you. But, so we don't waste time in the video, I've already prepared this in advance, and I want to use it. This is what I prepared beforehand, and now it's in the form of an array. But so that we don't get involved with arrays in the C language, I just want to put these numbers directly on the port. The point here is that, just to have a shorter code, the numbers are in hexadecimal, but like the previous project, it's enough for you to do the conversion yourself. For example, right now for the number 1, we have hex 0x06. Hex 0x06 is what we have. It has a 0 before it, meaning 4 zeros, and then after that 0, 2 ones, and a 0. So we see that for the number 1 we have exactly this. We have 4 zeros, a 0, 2 ones, and a 0. And these are exactly equivalent. Now what am I going to do? Again, I'll make a copy of this. And I'll place them in order. I want it to first display the number 0, then 1, and so on up to 9. We need another copy here as well. For the number 9, and for now, we don't need this array anymore. This is also one of the uses of this section of ready-made codes, where you can add some pre-made code for yourself. So now if I run this code, you'll see that it starts counting from 0, goes up to 9, and then returns to 0 again. Right now, in the simplest case, we have a counter from 0 to 9. If you want it to go beyond 1 digit, like 2 digits or 3 digits, then it just becomes a matter of C programming. But right now, we don't want to focus on the C language aspect. We want to better understand how the components work together. And so right now, we have a counter from 0 to 9. Now we'll add a little bit of C language flavor to our code so we can use our button as well. What am I trying to say? I'm trying to say that if pin A is 0, if you remember, I said that we use pins to read input. In the previous session, I clearly stated that if the value of pin A becomes precisely 0, meaning the button is indeed pressed, then it should proceed to perform this essential counting operation. That's it. This is the simplest condition you can use. So we don't have to get involved with the C language for now. So we set a condition. If pin A's value becomes 0, it should count from 0 to 9, and then we compile this. Now if we proceed into Proteus, we will observe that when we execute the simulation, absolutely nothing occurs. If I press this particular button just once, it meticulously counts from 0 all the way up to 9, and then definitively stops at the value of 9, primarily because it returns back to the very beginning of the operational loop and subsequently reaches this specific condition once again. If I press the button again, it starts counting from 0 to 9. You can keep practicing this counting as an exercise for yourself. For example, something very simple is that after it counts to 9, it turns off again. Well, turning off the LED means that those pins become 0. So all you truly need to do is, immediately after this particular condition, instruct it to precisely set port C to a value of 0, or to set it equal to 0x0, or alternatively to set it equal to 0b0. These don't have any difference from each other, and by now you should have completely understood that. Alright, I'm going to compile this. Now what happens is that at first it's off. When I press the designated button, it meticulously counts from 0 all the way up to 9 exactly once, and then it automatically turns itself off again until I press the very same button once more. And just like that, you can gradually add a lot of details to your projects and even implement very simple projects in a much more elegant way. That wraps up our 4th session. I hope it was useful and that you enjoyed it. In the final session, we'll look at something together that is almost impossible to achieve with just circuit design, or at least very difficult. For example, you might say that with light shows, we can create them using circuit design. With circuit design, we can have a counter on a 7-segment display. But in the next session, there is a component that really requires a microcontroller to work with it. So until the next session, goodbye.